Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture video 11. I had the wrong number in the last one, so please forgive that. We are in part 5 of chapter 3, and this is one-factor experiments or one-way Anova. So we've reviewed the hypothesis statements, the models, the assumptions, and in this video we're going to continue with checking the assumptions, which are very important. We've talked about the essence of one-way Anova, which is the decomposition of the sum of squares differences, or total sum of squares error, or total sum of squares differences, into the sum of squares based on treatments, and then the sum of squares that's left over we call sum of squares error because it's not accounted for. Large values of the sum of squares treatments reflect larger differences in the treatment means, which support our alternative hypothesis. Small values of sum of squares treatments means that SST is, this would say that SSTRT is approximately the same as SSE, and so their ratio would be approximately 1, which would give us an F value of 1, and this would say that our null, this supports our null hypothesis. Okay? So in the last video, we started checking assumptions, and we talked about the normality assumption, and we use a QQ plot to do so. Now we're going to talk about the assumption of constant variance, or equal variances, for each, wrong type of 4, for each, in this case power level, but each treatment level, okay? For each treatment level, or XI. So remember that for every value of X, we assume that there is a normal distribution for each of these values. Okay? So we want to talk about this equal variance or constant variance. We're going to also look at how do we determine if the observations are independent of each other like they're supposed to be. Do we have a good fit for the model? Okay? So this Anova usually represents a straight line, depending on what variables you've included. And then we may not have that correct model. It may not be a straight line. We may need to modify it, and we use regression to determine that. And then if we have a violation of the constant variance, how do we correct that? And there we're going to use variance stabilized transformations. Also, we're going to use, we can use some of these transformations to make the model a better fit. So if we transform the Y or the X or both, okay? So we'll talk about that as well. So we're looking at residual plots. And this is the key note here, that they should be structureless. There should not be any obvious patterns, okay? And a thicker or thinner tail in the distribution of the residuals is a much bigger concern than if we simply have a skewed residual distribution, okay? So we can handle the skewness a lot easier than we can handle the thicker or thinner tails. So we're going to look and see whether the different groups or treatment levels have a similar or a noticeably different amount of variation. If there's a funnel shape would look something like this, or in reverse, it could look something like that, where the variance at one treatment level is bigger, and as you increase or increase the treatment levels, you get a smaller variance, or vice versa, you get a larger variance. These funnel shapes are very serious issues that we have to address, okay? Then, in this, we look at the residuals versus fitted plot, which is this plot here, to see if we have this funnel shape or we have this type of funnel shape. So we could have that or that. So either one is a funnel shape. We go just a different direction. Okay. Now in the scale location plot, we're going to look to see if the edge points are very different, if there's an increase or decrease in these edge points. So yeah, so we'll take a look at that as well. So let's get started. Let's take a look at this plot on the left, and we do not see any funnel shape with these exterior points. We don't see something, going like this that doesn't fit this. What we see is, and you'll notice that this line is supposed to be flat and near zero, okay? Because the residuals have an average of 0. So if there's a difference then in these residuals, then you may see, if there's a location shift, then you'd see this line do something like that maybe. But it's a nice flat straight line, so that's a good indicator. We don't see a pattern or structure to these residuals. We only have, these are fitted values down here, so these are the y hat I values. And so when we fit with only certain values of x, every time x equals 160, you're probably going to get a fitted value close to 550. When x is 180 watts, you're going to get something 570 or something 560, 570, 580, somewhere through there, whatever this value is. And then for x equals 200, and then for x equals 220. Those were our 4 levels or factor levels or treatment levels that we have in this experiment. Okay, so we don't see that one group has a vastly different spread from the others. And again, this red line is flat and centered at 0. So that's a good thing. Now, here is a trickier plot. And what they've done is they've taken the residuals. Here, these are residuals, not standardized. So you see it just says residuals, and you can tell the values go up to 30 and down to negative 30. Definitely not z-scores. So here we have the z-score. We've standardized this. Z is equal to x minus mu over sigma, or z is equal to x minus x bar over s. And remember that the overall mean of the residuals is 0. It has to be. They are deviations from the overall mean, and so those deviations from the overall mean, the sum of x minus x bar equals 0. And the residuals are, in this case, I'm saying x, but we're using y's here, but it's the same, just switch out y's and x's, okay, with the formula. And so the mean is 0, so what we've done is we've taken y residual minus 0 divided by the standard deviation of the residuals, okay? And then we've taken the square root of this. And by taking the square root, it emphasizes, it exaggerates the difference here. And so what is not easy to see in this chart as a difference between the variations and the location is very easy to see here. So this should be a flat line, flat red line, if I can draw it, at 1, okay? And so we see, if you draw that line, you see that we have some slight variation. I'm going to use a ruler because I can't seem to draw this very straight. And maybe about there. Okay. And so by drawing the line at 1, it helps us see that there's less variation than we might have thought away from 1. Again, it's exaggerated. We see now that the first group has a noticeably smaller deviation than the other groups, or so it seems. All right, but this, remember that this is the actual, we're looking at the range here. So when you're looking at the range, that can be misleading. We have this one point that's far away from the rest here. So these points have a smaller amount of deviation. And then this is fairly consistent. Looks like there's, let's see, 3, 4, 3, 5. So it looks like here there's actually 2 observations there. And 1, 2, 3. And we have 2 observations here. And then we look at this one, and we see that these 2 are grouped, these 2 are kind of grouped, and this one's kind of by itself. We see a little grouping here. So this may lead us to believe that there is something wrong with our constant variance assumption. Okay? So now when I look at this, I say it's okay. I don't really see anything that's of great concern to me. But that, again, is based on experience and doing a lot of these analyses. So I've given you a way to do this without having to rely on your intuition or with a lack of experience. So what we do is, as I said, level 550 or thereabouts, fitted line level 550, they seem to have a smaller level than the other, smaller spread than the other 3 levels. A formal test for homogeneity of variances or equal variances was performed. We did that before, and we confirmed that the variances can be assumed to be equal. Our p-value is a 0.8977. So I'm looking for that here. Okay, so let's look at that test. I have the slides out of order. So this was the test for equal variances. And so I use Levine's test because Levine's test is less sensitive to departures from the normality. In fact, what it's doing is it's using the median instead of the mean for the center. And that means it's less influenced by extreme values, which is a good thing. Okay? And when we perform this test, we see that our p-value is 0.8977. So let's think about what this means again. Our null hypothesis is that the variances are equal. Remember, we can never prove the null hypothesis. We can show that we can reject the null in favor of the alternative when the type 1 error is really small, or the p-value, the probability of making a mistake, rejecting the null when it's actually true, when that p-value, and the p-value is that the null is true given the assumptions, right? So it's the probability of obtaining that extreme of a sample when the null hypothesis is actually true. So what this says is the p-value equals the probability of obtaining a sample value statistic that is as extreme as the one we obtained under H naught, or when H naught is true. So we're saying there's a 98.77% chance that we could obtain this value, this F value, so that's the F value, the actual statistic value, given that H naught is actually true. That's 98.77%. And so we could also think of that as a type 1 error, that if our type 1 error was, so the type 1 error would be rejecting H naught. Remember, type 1 error equals the probability of rejecting H naught given H naught is true. So if we rejected H naught, we would have a 98.77% chance of making an error in this case. So that means that it's very good. We feel very confident in assuming the null hypothesis is in fact true. Okay? Now, if we had a p-value of 0.15, we would not be feeling so good about whether we should accept or reject this null hypothesis, okay? And so we would go back and rely on these graphical methods more, okay? All right. But this has confirmed my opinion that there is no issue with this graph, even though it's not almost perfect like this graph on the left. Okay, so now we have something called constant leverage, and these are the standardized residuals plotted for the x values, the factor levels, the combinations of the factor levels. So at 160, 180, 200, and 220. Okay, it's going to look extremely similar if I did this with the fitted values. Okay, so the scale would look like this now if I did that. And again, you see this line in the middle that's really close to flat and at 0, so that is exactly what we expect. Okay, and this tells us that the average of each of the factor levels, the average residuals of each of the factors levels, is very close to 0. In fact, I think it's to the order of 10 to the negative 14th when I looked at the actual values. So they're very close to 0. Now, they've labeled the three most extreme points here, here, and here. This labeling does not imply anything about these points except that they are considered the most extreme out of the three most extreme out of all of them. It will label these 3 points regardless of whether there's an issue with them or not. Okay, and these charts, we always get these labels. Here's some, here's one, and I think there may actually be 2. Let's see, is that right? Yeah, so this is actually number... so here's 3, here's 7, and here's 1. And now because we've standardized this and taken the square root, we end up with a positive value. And so 3 and 7 are nearly on top of each other here in the square root. Okay? So here's 1, 3, and 7 again, the most extreme points for our residuals. And what we're looking for in this is there some shape? No, I don't see a funnel shape. I don't see a sinusoidal shape. In fact, I don't see a move in the location. This is talking about the location of the center, or the average, if you will. And I don't see it moving, okay, because it's a flat line and it's near 0. And then I look at the edge points, and I might see a slight decrease, a slight increase, a slight decrease. So going from this direction, a slight decrease, a slight decrease, a slight increase. Okay? I don't see anything that's drastically different. They don't appear to be far from the other observations. And again, we see a fairly consistent spread across the different levels of power. So again, we are good that there are no real extreme points. So depending on this chart, if you have a point that's really far away, not only are you saying that you may not have constant variance, you could be identifying a leverage or a outlier. Okay, a leverage point means that it has a lot of influence on the result of the test. Okay, so it's very influential, or it has a lot of leverage, if you will. Okay, and then if we were to see, we could see a straight line in the middle. Oops, pretend this is a straight line. And we could see that we had a funnel shape. So again, the mean is real close to the center, but then the edge points are showing that we have a shape there. Or we could see, if we had something like this, so it would give us a shape. Any shape would be an issue, okay? So we're not seeing that here. So I think with that, along with our verification using a formal test, we're very confident in saying these are there is not an issue with our constant variance assumption. Now, how do we analyze for independence? Okay? So independence, you have to use the plot that we could use is the plot of residuals versus time. But to do this, we have to have the order of the observations. And we don't have that. Okay? So these were not run in the order in which they are in the data set. In the data set, all of power of 160 were put together, and that is not how it was done. I do not have that, but the author did, but unfortunately he didn't give it to us. So all I can do in this case is just look at the order that he's given us and analyze this to show you the idea. Okay? So what it says is we should not have a tendency to have, so it says a tendency to have runs of positive and negative residuals indicate positive correlation. That implies that they're not independent. Okay? So there's a rule that says if x is independent of y, then rho is equal to 0, the correlation coefficient. It doesn't work in reverse unless it's normally distributed, and we're assuming normal distribution, so it does work for us here. But so we need rho to be the correlation coefficient. We need that to be 0 or close to it, so that it's statistically not different from 0. Well, we have to be very careful here, and I'm going to draw lines to show, oops, not a very good line apparently. I'm going to show the order here, and then this comes all the way down to here, and so this is really the only way that I could see which observation came in the next. So the order of the observations. Very difficult. The points are very close together, at least for me, to tell what is the order of these observations. And so this, and then this. And so when I look at this, I need positive runs. That means here I have, I'm going to change the color here. Here I have two residuals that are both positive. Okay? But then I have a negative, a positive, a negative, a positive. Now I have two negatives in a row, then a positive, then two negatives in a row, and then two positives in a row, then a negative, then a positive, then a negative, then a positive, then, oh yeah, I did the lines wrong there, didn't I? Interesting how that's okay. And then this goes to here. Okay. So I was up here positive, negative, and then positive, positive, so two here. Two observations is not a run, just so you know. We would expect, at least 3 or 4 in a row. And we would expect to see some positive 3 or 4 in a row positively or more, and then 3 or 4 in a row negative or more, 3 or more negative at a time. And we don't see that. This fluctuates very nicely up and down, up and down, up and down. So this tells me that we do have independence. There's no obvious pattern to these points, as you can see, and it's easier to see that by drawing the lines. I'm going to get rid of the green so it's a little easier to see. Okay, and now I'll correct my error here. Okay. Okay, so when I look at this, I see random fluctuations above and below the lines. I do not see any trends which would indicate correlation. Okay? All right. So if this occurs, it is a serious problem and it's difficult to correct. Basically, the only way you can correct this is to rerun the experiment in a randomized order. If the experiment is very expensive or time-consuming or both to perform, then you've wasted all of that money and time on something that can't give you a result that you're looking for. Okay? Can't tell you one way or the other. So that's why they say it's difficult to correct, because really the only way I know of to correct it is to redo the experiment. So it's very important. This randomization and the order of the experiment is extremely important. Someone may say, well, it's more expensive to do that randomization. We have to do these setups or changeovers or what have you. But if you don't do that, then it's very likely that you're going to have dependence. And so the results of the test will be meaningless. All right. So again, the proper randomization when you're designing the experiment is a key to obtaining independent results. All right. So what if you found out that you didn't have a constant variance, or you didn't have a good fit? Okay. So what we would do, and we're going to see how we look at the fit in just a minute, we would apply what we call a variance stabilizing transformation. Some of the very well-known variance stabilizing transformations for other distributions, for Poisson, that would be counts, for log normal, and for binomial. You say, well, we're talking about normal distributions here. Yes, but there are special regression and Anova models for a Poisson distribution, a log normal, and a binomial. Okay, the binomial, we usually make a logistic regression, so that's a special case of binomial, and we could use this transformation. So we've given the transformations. Just why do I have a +1 here? Well, because the log of 0 doesn't exist. So if you go down to zeros, and you can't take the log of a negative number either. So you'd have to have positive observations, and you'd have to, if 0 is in the values of y, then you can't use a log. You'd have to use a y plus 1, and you can't just do it for one observation. You have to do it for all. The Poisson distribution is the same. It could be the square root of y, or it could be the square root of y plus 1 to keep you away from 0. Okay? And the most likely transformation you would use for normality would be the Cox transformation. It transforms the data into a normal distribution, but it is a little more complicated. I have pasted this from Wikipedia on their Cox transformations. And so we have the 1-parameter Cox transformation and the 2-parameter Cox transformation. So these are the transformations you'd have to apply. Now, there is a package in R that will do this that has functions that will do this for you. So we're not going to take the time to cover that right now. That is something I need you to know is out there. You may have to use it, so you may have to investigate this and do a little research in real life to make sure that you have good, reliable results. Okay, and you may have to transform not only the y values, you may also have to transform the x values. Sometimes you can look at the shape and say, well, I should transform. Once you get used to these transformations, you say, oh, if I just transform the x values, I'll be fine. Or if I just transform the y values, I'll be fine. Or no, I need to transform both. Okay, and so there's quite a bit of trial and error until you get used to these transformations, and even then there might be. So these are not the easiest things to implement sometimes, and the problem is if you take the arc sign of something, what's your interpretation now? You see, so usually you'll want to transform back to the original units when you get your results. So it makes some of the explanations to others extremely complicated and very difficult to understand in some cases. So we want to avoid transforming the variables as much as possible. Okay. So we want to know if we have the right model. What do we do there? Well, we can think of Anova as a regression model. Okay? And there's two different ways to think of this. I'm going to use just the regular regression because that's what our book used. So we're just saying that power is now a continuous variable, which it is. We just chose 3 values of it and limited ourselves to that. So instead of making them indicator functions, meaning 0 or 1, we're just going to say that power is continuous and set up the relationship the etch rate equals power. So what we're saying is y is equal to a, which would be our intercept, plus b times power. Okay? And, oh, that's right, we are using alpha and beta in this class, so that's fine. Alpha plus beta times the power, plus the error. Okay? And so that would be our model. That's what this says. Okay? And you have to tell it the data set, or you could put in front of each y0 $sign. You'll notice I'm using y0, not y1. The reason for that is y1 set the power to factor levels, and this won't work for y1. It will force us into indicator variables, which is not what the book did, nor what we want. That would make it very difficult for us to fit a quadratic equation to this. Okay? And so I have used the summary of Reg 1, Regression 1, which I've set up here. And what I did was I set y, I think this is redundant now. I think I did it, yeah, I did this in the code earlier and forgot to remove this. But y is a data frame, and it has power as a continuous or numeric variable. Okay? And so when we do this, this is just the output as R gives it to us, not always pretty. Okay? So it tells us the formula we used. It gives us, for the residuals, it gives us the 5-number summary that we could use for a box plot. Coefficients, so here we have the intercept, so alpha, and then this is beta. So it's the intercept for power. And it tells us how significant the p-value is here. It's way less than 0.05, and look how small this one is. So power is extremely significant in estimating the etch rate, and the intercept is significant too. So that tells me that if the model fits, this is a good model. Okay, so it says that the data are linearly related, but let's take a look at some plots. So what I did here was I plotted this power and etch rate. Power is X, etch rate is Y. Change the labels, and this is for the type of dot that we have there. And then I put the ab line, which was for regression 1. So this is the best fit line through these points. And so notice that this is, so the center here would be somewhere like that. That would be the center of that one. The center is probably right there, very close to this. But the center of this is somewhere in this area. And the center of this one is probably around there. So the line fits better for the lower values than it does for these upper values of power. It doesn't fit that well. So let's fit a polynomial, a second order polynomial. So we'll have a square, quadratic equation, if you will. And so I've given you the code to do that here. And what we've done is I've said this is regression 2 so that I have a different, and I found this code on the internet, and so we make it a polynomial, and we're using the variable power, and we're saying a second order, or squared, okay, term, put that in there, and we're using raw data. Okay? and then we're telling it which data frame to look at. And so to get this quad line, or quadratic line, I'm going to clear this out so we don't have so much mess. So we're taking reg2, the coefficients, and the first coefficient, which is, this first coefficient is alpha, or the intercept. This is for x equals power. So let's say x1 equals power. So this is beta 1. And then, see, so here's power. And then here, this is the coefficient, we'll call it beta 2, and where x2 equals power squared. Okay? So we have a second order polynomial, or a quadratic equation here. Okay? And so I've saved this quadratic line so that I could plot it. So I'm going to plot the power in the x, the h rate in the y, and then I put in lines, and I want power as the x and quad line as the y. Now, for some reason, this also prints out my initial regression line, or I could say the linear regression line. And this would be the quadratic regression line. And you'll see now that both of these are near the center. Now this is much closer to the center. This is much closer to the center. And this is near the center. If we look back up here, yeah, so I'm not sure. Oh, what this is this is just a straight line. So this is a straight line between the first and the last. Between first and last groups, or treatment levels. Okay, and this is the actual quadratic line that was fit. So this shows you the deviation between just a fit between the first and the last and the quadratic line. And you'll notice that all of these are much closer to the center if you're looking at this bottom line here, that all the points there are now much closer to the center. So that tells us that the better fit would be a quadratic. So that would be a better fit than the linear equation we have. We're not going to go back and do that, but we could. We would have to make a few more variables so that we could apply, well, yeah, so what we would have to do is make a power squared and then fit that in the Anova. So we would make it a two-way Anova to do that. Okay, so we're not going to do that. All right, so we have finished looking at the assumptions, the analysis of the assumptions, and we have talked about a few of the ways to correct things. So including these transformations that we could use here. So we could transform the data, usually the y values, but it could be the x values. And so in our case, we may want to, I didn't put the line, the equation of the line here, but we may want to change this to a two-way Anova and use power and power squared. And then perform the Anova that way. But interpretation would be a little more difficult, wouldn't it? It's a little more difficult to explain this a quadratic line here than it is just a straight line, right? So we could do that and correct for the shape. But again, that's not a variance transforming, that's not a variance stabilizing transformation. So it would probably be better for us to come up here and use the Cox transformation. And again, there's a package in R that has this as one of the formulas so that we could just use it as a transformation. The problem is we'd want to do an inverse transformation of the values at the end, okay? which again is beyond the scope of this course. All right. So if you run into that, we're going to learn some non-parametric methods, and they're a lot more simple and easier to understand than the transformations that we're talking about. That's it for this video. I hope that this has been informative, that you know more about how to check the assumptions. And again, if you don't check the assumptions, then you don't know if your output has any value, that your analysis may be completely meaningless, but you might be lucky, it might be right, or you might be unlucky and it might be completely wrong. So you have to check these assumptions, and if there's a violation, you may have to do something different, or you may have to use a non-parametric method. Again, we'll talk about how to do those later on in the course. If you have questions, come to virtual office hours. If you can't make it to virtual office hours before you need help, email me, and I will get back to you as soon as I can, all right? The most reasonable time that I can get back to you. Please take care of yourself. Stay safe, because we want to see you again next time.